And I think we're in time for the next speaker, who I hope is online with us. This is Professor Joe Ball from Virginia Tech, and very happy to introduce him this evening. For me, this is the evening. And he will speak on pairs of commuting contractions, Endo lifts, and function models.
Thank you very much. I am here. Can I share my screen? No. There we are. So it's a pleasure to be here for this honorable occasion. And my talk also involves dilations, but it's in the sense of operator theory, not in the sense of function theory. And this is joint work with a young fellow from India, Haripada Sal, who has been working with me for the last few years. And it's about I've just learned now that there's this paper of Endo that's the most cited operator theory paper from Acta Szeged. And you see Endo's name here, it's connected with that paper. So it's about the dilation and lifting theory began with the work of Nagy and Foyage from 50s and 60s. So I'll review what's the single variable case, and I'll talk about a particular approach of Ron Douglas, which then is the model for how our approach to the two variable case, which is the Endo dilation theorem. So just as a way of setting up definitions, we're talking about T is a contraction operator on the Hilbert space, and we talk about a unitary dilation if this compression of the powers, positive and negative, gets you back the appropriate power of T, T to the end if n is non-negative, T star to the end if n is negative. And it just means that the space H is embedded into the space K tilde in the middle in this matrix decomposition. And the matrix decomposition for U is this lower triangular form with T on the central diagonal. So that's the structure of it called power dilation. And then the famous result of Nagy, which is in the appendix to the functional analysis book of Nagy, or I'm not sure where it first appeared. No, it first appeared in the Acta Szeged, I think. Any contraction operator has a unitary dilation, and a finer analysis says that it's if you insist on minimality, then it's unique. And there's a now famous corollary of this, the von Neumann inequality, says if P is a polynomial, complex coefficients, and you take polynomial in T, operator norm, it's bounded by the supremum norm of P over the unit disk. And the proof is just this one line. If you use the Nagy dilation theorem, you can represent T as the compression, polynomial in T is the compression of polynomial in U. The norm of this compression is at most the norm of P of U, but for U unitary, you have a spectral theory So the norm of P of U is at most the sup norm of P over the unit disk, and the maximum modulus theorem over the unit circle. So that's the sample application. And then in practice, we work with isometric lifts. So we have the term lift. It's related. So first of all, it's only an isometry, it's not invertible. So we have only non-negative powers to work with. So you compress these on the bigger space K, and you compress the power of V to H, you get the power of T. And then you also ask that H is invariant for V star, and then V star restricted H is the same as T star. So this means that V has this T embedded in a matrix representation for it when you represent it on K equal to H direct sum H perp inside K. And now one often sees the terminology coextension is used rather than lift because it's less confusing sometimes. Then there's a close relation with unitary dilations, meaning if you have a unitary dilation, you restrict the unitary dilation to the powers of U on H, non-negative powers. That restriction is V, then V is a minimal isometric lift for T, and conversely, if you have the minimal isometric lift, it's not hard to embed it in the minimal unitary dilation. So it suffices to focus on isometric lifts, which is what I'm going to do. And then for further flexibility, it's convenient not to insist that the space H is a subspace of the space K. You indicate explicitly an isometric embedding operator. Pi maps H into K, just embeds H into K isometrically. And you ask that V is an isometry and that V star pi is pi T star. This is the lifting property. And then you will also have it dilates in this sense up to after you take account of the embedding, then you have powers of V compressed to the corresponding power of T. And now it's a little proof. And then as a illustration of a construction, there's a so-called Douglas isometric lift of a contraction operator. It's his paper from the 60s when he was in competition with Naj Foyester. This was just in the air. So given the contraction operator, we let dt star be this defect operator of T star, and calligraphic dt star is the range of the defect operator. Then there's a standard map from H into the H2 space with coefficient space defect range of dt star given by such a formula. And I have this peculiar notation because I think of it as an observability operator coming from a state output linear system. You run a system, the state update is with T star. The observation is to apply defect T star to the state at time N. Then the initial state to output map is the observability map, and it's given by this very formula, which is what ODT star T, observability operator DT star T star stands for. Then this operator comes up in model theory. Jim Ronak, who's in the audience, I saw, and has the key intertwining property, the backward shift. So it maps into a Hardy space, whereas it's a shift operator. Then the backward shift on the range observability operator, the observability operator applied to T star. So that's the, this is the beginnings of how you transform a contraction operator represent a contraction operator with certain properties as the backward shift on some subspace, backward shift invariant subspace of H2. So we do this, and let us compute the norm of this observability operator applied to a vector. So it's the sum of the norm squares of the coefficients, Taylor series coefficients. You plug in what dt star is and write it as the quadratic form. Then this series telescopes so that you get norm x squared minus the limit tn t star n xx, and t is a contraction, so this tn t star n has a strong limit, which I'll denote as q sub t star squared. So I can denote its non-negative square root as q sub t star. And I'll take calligraphic qt star to be the range of qt star. Then it satisfies this identity with respect to t because of this, you just run it through this limit. And then the operator x star on this space qt star makes sense to define as qt star x goes to qt star t star x, and this is an isometry. And it satisfies this operator identity. Then a elementary operator theory fact is any isometry can be extended to a unitary in a larger space. So I extend x star to a unitary, which I'll denote as w sub d star, d for Douglas. And the larger space we'll still call qt star. So that's a space containing the range of the original Latin qt star operator. And this will have its own intertwining property, wd star qt star equals qt star t star. So this is a big deal for our lifting problem, because then if we define pi d, the Douglas isometric embedding map, takes you from our original Hilbert space H to this direct sum space, party space over defect space T star, and this limit space QT star we just constructed by this formula, column observability operator with operator QT star. Then when you apply pi d to T star, then the intertwinings we have already noted, you have diagonal mz star, wt star coming out. And this mzwd, mz is a shift, so it's an isometry on H2, and wd was constructed to be unitary. So this is just a unitary with this decomposition exuding the Wold decomposition. And pi d intertwines T star with the adjoint of this isometry. So this pair, pi d mzwd, is by our definitions an isometric lift. It's going to be essentially unique. And this appears in Douglas's 1968 paper, not quite in this form. And so we call this the Douglas lift. So for the single, so that's a proof, actually, different from the original Naj proof or the Naj-Foiach proof of the lifting theorem for a contraction operator. And I said this, and you can make it, so I think of this as a functional model for the lift. So the second component was rather abstract, but you use spectral theory to represent WD as a multiplication operator on a L2 space of the unit circle. And so you can think of this as also giving you a functional model for your lift. Then what we're really interested in is the Endo dilation theorem, where you start with a commutative pair of contraction operators and you want to lift to a commutative pair of isometries. So for a single isometry, you can think of the Wold decomposition as your functional model. You have the first piece is multiplication by a coordinate function on an H2 space, and the second piece, you have spectral theory for a unitary operator. So a paper from 1978, which I actually didn't learn about till much later, is, and Harry Bergovich has also worked with this. You have a functional model for any pair, commutative isometric pair of operators. And the ingredients are a coefficient Hilbert space F, a second Hilbert space K sub U, in case there's a unitary part. Then you just have whatever two operators you like. P is a projection and U is a unitary on the coefficient space F. And you have two unitary operators on the Hilbert space KU, which are commuting. So that's not much of it. So given those ingredients, we form the space, Hardy space over F, and this second space KU, and we have this pair of operators. So V1 is on the H2 part, and it's not multiplication by Z, but it's multiplication by this matrix operator pencil, which makes sense. For each Z, you take F into F, so you multiply by that point-wise, and you have a multiplication operator. And there's a companion where the U and the P's are rearranged, and the rearrangement is such that when you multiply these two together, I don't know if you can do it in your head or not, then you just get multiplication by Z. So the idea of the Berger, Coburn, Lebeau is to represent a pair of unitary operators commuting by taking the model for the product operator. And so the product operator is just multiplication by Z, and then we just assume the W1, W2 tag along as part of the data. These are the unitary part if present. If the product is not a shift, then you have the second part. And then the result is that any commutative isometric pair is unitarily equivalent to, concretely, this pair represented in the model. So I write M1 and M2 shorthand for this multiplication by the pencil parts. And so the data is just coefficient space, projection operator, unitary operator on that space, and a pair of commuting unitary operators on the second space. And that's what any commutative isometric pair looks like. And the implementing unitary identification map can be taken, you can identify F with the defect operator for bold V star. Bold V is the product of your two commuting isometries, V. And KU is the same construction as in the Douglas model, but with the isometry V instead of the contraction T. So we have the QV star. For the isometry case, it turns out to be the intersection of the ranges. And so this is just reproduces your Wold decomposition. The Douglas construction for a isometry just gives you the Wold decomposition, amazingly enough. And it's our old friend, observability operator based on the effect operator in the Q sub V star. So then you just take the model for the product of V's, and then you figure out what the factors have to be so that they also commute, and the product is MC. Then you get, that's how you get the model. Then there's a nice unitary equivalence. suppose one or two such models unitary equivalent, well, if and only if the corresponding data are equivalent. And equivalence for the data is there's a unitary transformation between the coefficient spaces, FF prime, and between the unitary parts, HU, HU prime, so that the prime P is unitary equivalent to the unprime P, prime U is unitary equivalent under the same unitary to the unprime U, and the tau U gives a unitary equivalence between the respective W's. It's just completely natural. So it's a good model theory. Now we go to two variable lifting theory, which has the name Endo, from the famous paper of Endo from 1963. So we're given a commutative contractive pair T1, T2 on a Hilbert space H. And then I want to talk about an Endo lift, meaning it lifts to a commuting pair of isometries. And I want to not insist the lifting space K contains H as a subspace, but I have a identification map to go from H into K. So I have the data for the lifting is a pi and a pair of commuting isometries on K. So pi is just an isometric embedding H into K, and V1, V2 commuting isometries on K. And the lifting property is that the range of pi is invariant for the adjoints of the isometries, and you have this intertwining property which gets you back to the adjoints of the contractions. And then you'll have this form of the dilation property also. And then Endo's theorem is that you can always do this, take any commutative contractive pair, there's existing Endo lift. But we're still talking about it because in general, people were not happy with its construction. It's sort of a brute force, big block matrices, unitary extensions of unitary extensions, and difficult to work with to identify additional structure. So our goal is to improve it. So the tool for the construction, so it's going to be like the Douglas lift for the single variable case. So then it also incorporates the Berger, Coburn, Lebeau model for the commuting unitaries. So the notion of a pre-Endo tuple is a coefficient space F, and a lambda PU. So P is the projection used unitary on F, and lambda is an isometric embedding operator at the level of coefficient spaces. You just go from the defect space to the coefficient space F. So in the Douglas case, this was just the identity. We're building an H2 space built on the defect space, and the embedding was the identity. Defect space and the defect space considered as the space of constants in H2. And so you say, now we have two contractions, so what's T? Well, T is always the product in either order they're commuting. So T star is T1 star, T2 star. So you're taking defect space of the single contraction operator, product T1 star, T2 star. So this looks reminiscent of BCL tuple. The BCL tuple was just FPU. And then for what we're calling the pre-Endo tuple, there's extra information involving the commuting contractive pair, T1, T2, namely you have to have an embedding of defect space T star into this coefficient space F. That's all it takes. And we have a notion of unitary equivalence. which extends the notion of unitary equivalence of BCL tuples. Namely, the extra green is that the tau applied to lambda gives you exactly the lambda prime. So the lambda and lambda prime start on defect space for T star, and then the same unitary, giving unitary equivalence between PP prime, UU prime, also moves you from lambda to lambda prime when applied to the range of length. Then there's a notion of minimality, which is natural. Namely, the space F should be minimal, as small as possible, given you're stuck with what lambda is doing. So the smallest subspace, so here's the first typo. Smallest subspace of F, which is invariant for P, reducing for U, and contains range of lambda. That should be rather than range of P. Should be all of F. Then that's, so we may as well cut down to F0 and not change anything. So this is the notion of minimality, which will tie up with minimality for the Endo lift. So we're, but unfortunately, there's another notion of minimality called strongly minimal. So given a pre-Endo tuple, then we have the pure part. We threw away the unitary part, W and W2. That's a BCL tuple. So associated with that are the model operators, multiplication by the two commuting pencils, whose product is multiplication by Z. And then it's not hard to see that the operator theory interpretation of what I call minimal for the pre-Endo tuple is that the smallest joint reducing subspace for the M1 and M2 containing H2 with coefficients just in the range of lambda will get you to all of H2F, namely MZ. The product of M1 and M2 is MZ, and this space is invariant for MZ. You don't go anywhere beyond that. But when you multiply by M1 and M2, you have these operator pencils which move things around, and then the minimality condition is that when you do that moving around, you get all of H2F. But we'll need a notion of strongly minimal. Namely, it could happen that the smallest joint invariant subspace of M1, M2 containing H2 rings name is all of H2F. So it's a tautology that strongly minimal implies minimal. And then unresolved open question 1, does pre-Endo tuple minimal imply pre-Endo tuple is strongly minimal? So it's frustrating. You try to write down any example you try to write down of a minimal guy turns out to be strongly minimal, yet you can't cook up a proof to show that minimal implies strongly minimal in general. That's the kind of, and it's not deep enough that it should be undecidable or anything. So we're stuck with that. So I did this. Then I had this prefix pre attached to all this. So now to define Endo tuple, for the moment, you don't see why I want this. But given a pre-Endo tuple, I'm going to say it's actually a true Endo tuple if two obscure operator identities hold. They either hold or they don't hold. And again, we can't prove that there are examples where these don't hold. Every example we cook up, they do hold. So this will come back later. This is related to the lifting equations you need in the model. So now we have a definition of endo tuple for T1 star, T2 star. And I need a little bit more about the unitary part. So we go back to the Douglas embedding operator, and it has this intertwining. Pi dt star gets you the diagonal mz star wd star, pi d, wd star. WD was the unitary operator on this space, qt star, containing range qt, operator qt star, squared, which is strong limit of this t n t star n, powers of t. Then there's a useful factorization lemma. Assume you have t pi d w t on qt star as in the Douglas lift, but now t in turn has a factorization as t equals t1 times t2, where t1 and t2 is the commutative contractive pair. Then with that t, you plug it into the Douglas lift model, and you get this WD. Then the result is WD factors uniquely WD equals W1, W2, where W1, W2 is a commutative unitary pair on this space QT star, but it's tied together with the T1 and the T2 because you have to have these intertwining. W1 star QT star gives you QT star T1 star, and similarly, W2 star QT star gives you QT star T2 star. So the unitary part is rather simple to extend to two variables. This will amount to the two variable lifting property, everything you need. You don't have to take the space bigger, stay on the same space, and you have the lifting property for T1 and T2 via this piece of the second complement of the isometric embedding method. So that takes care of the unitary part. So the harder part is the shift part. Oh, so now the actual theorem. So I can write down the model. So all I need to write down a model for endo lift of a given commutative contractive pair T1, T2 is so-called minimal endo, strongly minimal endo lift of T1 star, T2 star. So given strongly minimal endo tuple, which was these ingredients, F coefficient space, P and U projections on F, lambda, the embedding of defect operator for T star into coefficient space F. Then our lift space is H2F, the old QT star. Our pair of isometries is as in the BCL model. And now the W1 and W2 are constructed from the product, which is WD. It's borrowed from the lift for the product. The Douglas lift, the Douglas lift for the product gives you the second components for the endo lift for the pair. And the embedding operator is almost the Douglas embedding operator, but you have to multiply, you use the lambda to embed into H2 with coefficient space F instead of H2 with coefficient space DT star. Then that's it. This works as a minimal endo lift for T1, T2, and it's everything straightforward, except we had to go to endo tuple, not pre-endo tuple, so you have to carry along those operator equations. So you need V1, V2, which was on the previous slide, commutative isometric pair, but the M1 and M2 are just in the BCL model form, so that computation you almost could have done in your head. You have a commutative isometric pair. And the second components are just the commuting unitaries going from the factorization lemma, so they commute. So that's easy. Then the lifting property, Vj star on pi should be pi Vj star. Then that again is two components. So the first component is this identity here, but that turns out to be the two operator equations. It reduces the two operator equations by use to define endo tuple versus pre-endo tuple. So that's true by hypothesis. And then the second component was this intertwining, which came out of the factorization lemma. So it's all easy construction. And then we must then to check the minimality. There's an intermediate step that this is a copy of the Douglas lift when you take V is the product of V1, V2, and you have N. So this is V1 to the N1, V2 to the N2 with N1 equal N2. That's what this V to the N is. Then there's a computation to see that you at least get this space when you take this much. And this space is certainly contained inside what you get when you take distinct powers, V1, V2 on range pi. And then there was definition of strongly minimal, not just minimal for the endo tuple, that this span will be the whole space. So this object, so given any minimal endo tuple, you write down a minimal endo lift. Then there's a converse. Any minimal endo lift for T1, T2, they exist by Endo's theorem, but what do they look like? They arise in this way from a minimal endo tuple, which is just this amount of data. Coefficient space, projection, unitary, and embedding operator unit. So let me just discuss this. How much time do I have?
I computed something like 13 minutes, but
oh, plenty of time. Thank you. Now I'll go twice as fast. So I'm just going to discuss the start of it. So this is very detailed in bookkeeping. So I just give a overview. So the bold pi V1, V2 is just completely arbitrary, abstract endo lift, which we'll eventually assume is a minimal endo lift for T1, T2. So that means V1, V2 is a commutative isometric pair, and which has this lifting property. This intertwining is the lifting property for J equal 1, 2. But it's a commutative isometric pair, so it has a BCL model. And it acts on the space H2D bold V star, Q bold V star, bold V being the product bold V1 times bold V2. And we discussed the unitary identification map, which takes the abstract lifting space to the functional lifting space, which has the same as the Douglas form, but based on the product of the V's. And the map is this observability operator in the cube. Then embedded in this lift is a lift for the single contraction operator, namely, this is the product. So MZ with coefficient space dV star was the product of those M1 and M2, and W is the W product of the W's. So this would be a this single operator is the Douglas lift for the product of the T's. Single contraction over T with the product of the T's. But this lift is not necessarily minimal. That's the whole issue here, because when you factor the V as V1 and V2, then you spin out more stuff. So we can restrict the lift space K to the minimal space for which, for the lift of just of the contraction T, the product contraction T, and that'll look like this. The space and the isometric embedding operator will have, this is the abstract embedding operator followed by the BCL unitary embedding act. Then this has range. This generates a space K-min. Then this is a minimal isometric lift. So we have a minimal isometric lift embedded in this big space. On the other hand, the Douglas lift is another such lift. So by uniqueness for lifts, there's two equations. There exists a unitary from the Douglas lift space to the minimal lift space inside our lift space, Endo lift space, K, so that it intertwines the associated single isometries, and it carries over the range space for the Douglas lift to the range space for the other identification there. So this is then working with this, the gamma naught hat considerably simplifies. It's a block 2 by 2, but it turns out the off-diagonal entries are 0. The 2 entry is unitary. So then QT star, if under minimality, so QT star is identifiable. QV star is identifiable with QT star, and then everything starts to look more like the model sending, and you can find the model. You can find your Endo tuple coming out of this stuff, and you have everything in the model form. And then the minimality assumption tells you that the Endo tuple that's embedded in here is going to be a minimal Endo tuple. So that's the idea. So this is very streamlined construction for our Endo lift, but there's one issue. The existence of pre-Endo tuples was easy because it was just a space and operators. You pick any Hilbert space, coefficient Hilbert space F, P was any projection on F, U was any unitary on F. And then you did need an embedding operator from defect space for the product T star into F. So that's, you can always do that, just require dimension F is big enough. Rank defect T star is lower bound on what you can take for dimension F. And it's just free and easy. Such things exist. But the existence of the Endo tuple requires something more. You have to also satisfy that pair of operator equations. Otherwise, you do this whole construction, but you have everything except the lifting property. So it's a cop-out. You don't have a reproof of the Endo theorem because you don't have existence. So there's something called special Endo tuples. So you just take a commutative, and I'm going to do this for T1, T2 rather than T1 star, T2 star. For the application of the lifting problem, you apply all this to T1 star, T2 star. So there's a whole and this is kind of formulas up here in Endo's original paper. He's using the same algebra somehow here. So if you take a commutative contractive pair, let T be the product, then you have these identities. Easy to check out. So in particular, dt2 squared plus t2 star d defect t1 squared d1. It can also be written with 1 and 2's interchanged. That just uses commutativity. You lose that if it's not commutative. So we introduce domain U0 is whatever the closure of this. It's written as a direct sum, but they're coupled because it's the same H in the original Hilbert space H. So this is a subspace of dt1, defect T1 direct sum defect T2. Similarly, you interchange T2 inside here and T1 inside here. That's another space. And a consequence of double star, if you define an operator U0 densely from DU0 to range U0 by this formula, it will be unitary. Choose a coefficient space F dagger. It contains the direct sum of these two, the formal direct sum, external direct sum of these two defect spaces. So it's the external direct sum of those two, external direct sum of third space, whatever you like. And you let U dagger be any unitary extension to F dagger of that U0. So this is always possible if the dimensions of the orthogonal complement spaces match up. So if they're finite and unequal, you just have to go infinite dimensional, but this can be done. And P dagger is any projection on F dagger extending the projection P0, which projects something in this direct sum to the first component. So you can always write such things down. Lambda dagger is embedding of dt defect T into defect T1 direct sum defect T2. This particular embedding, and as a consequence of the little identities in the previous slide, this is an isometric embedding. Then this object is a pre-Endo tuple. I have a coefficient space, I have a projection and a unitary on the space, and the embedding operator defect space of T into F dagger. So any such pre-Endo tuple constructed this way, we'll say, is a special pre-Endo tuple. And then the amazing result is that any special Endo tuple is in fact an Endo tuple. Namely, the two extra opera identities are automatic. And it just is surprising. You just crank it out and it works. I can't explain why it works. So therefore, you can always write down special Endo tuples by this tricky identities. And therefore, the corollary is the new proof of Endo lifting theorem, namely, write down any special Endo tuple that exist, and then use the previous results to write down a minimal commutative contractive, a minimal Endo lift for our commutative contractive pair. And so that gives us unresolved open question 2 of the same category. Is any pre-Endo tuple unitarily equivalent, at least, to a special pre-Endo tuple, which would imply that all pre-Endo tuples are in fact already Endo tuples. So this is the same category of the frustration. You try to write, you get up in this on one day, you get up, oh, I'm going to write down a counterexample, and then it turns out that your pre-Endo tuple is in fact an Endo tuple. And on the other hand, you try to prove that any such pre-Endo tuple is an Endo tuple, and you get lost, and you don't see how to go. Okay, so now I'm at the end. These were last minute slides, so I didn't get around to a conclusion thank you slide. So I'm just saying thanks for your attention, and I appreciate any comments, discussion. Thank you.
Thank you very much. Thank you. And indeed,